Module 4, Lesson 11, Factoring Expressions. All right, learning targets should look very familiar. We are going to be starting out taking a look at operations. So we've got one little connection to make there, relationship between operations, in particular looking at the relationship between addition and multiplication. We are going to also be comparing expressions. We are going to be asking, when are they equal? I can statements, I can show and explain writing equivalent expressions using the distributive property. So equivalent, we've got that equal concept there, distributive property, which ties into addition and multiplication. I can write expressions in factored form, which ties into the distributive property. Taking a look at an example here, and we're going to use the model to answer some questions. First question, how many 5s are in the model? Well, quick look here, 1, 2. And how many 3s are in the model? Quick look, there's 2 of them. So the question is, what would you write with words to explain what is happening in here? I have a couple of different thoughts kicking around in my head. The first one is I've got 5 plus 5 plus 3 plus 3. And of course it says to write it out in words, so 5 plus 5 plus 3 plus 3. That's the first thing I notice. The second thing I notice is that I've got 2 groups of 5 and 2 groups of 3, and I'm going to be combining them together. So the sum of 2 groups of 5 and 2 groups of 3. So I'm going to find the 2 groups of 5, the 2 groups of 3, and I'm going to find the sum of them. So if we were actually to write a mathematical expression to represent this model, using these words, 2 groups of 5 added to 2 groups of 3. Or, like I showed earlier, you could set it up as an addition model. Oops, sorry about that. Here is another model, and we're going to want to answer the same questions here. And I know that what's going to show up on my screen is different than what's in your workbook. I think there's a typo in the workbook. So at any rate, the questions are slightly different, but here we go. So how many 5s are in the model? Well, I look and I say, hey, I've got 2 5s here. And it's going to ask me how many 3s are there. And I look and say, hey, I've got 2 3s. And if I were going to write the expression in words, well, I've got 2 groups of 5 plus 3. Here's a group of 5 plus 3, and here's a group of 5 plus 3. So 2 groups of the sum of 5 and 3. And so what expression could we write to represent this model? Pause and think about that for a second. Here are a couple of ways that I could write that. First, 5 plus 3 and 5 plus 3. But you'll remember that multiplication is repeated addition. In this case, we are adding together over and over again 5 plus 3. So I could write this as a multiplication expression. 2 of 5 plus 3. 2 of 5 plus 3. So the question is, are these 2 things here, are they equivalent to each other? Do they represent the same value? Now, hopefully you can evaluate this without actually doing any addition, multiplication, or anything. Hopefully you can look and say, okay, I've got 2 5s here, and I've got 2 5s here. And I've got 2 3s here, and I've got 2 3s here. These models are representing the same value, which means these 2 expressions, I guess there's 3 of them there, must be representing the same value. So yes, they are equivalent because both expressions have the 2 5s and they both have the 2 3s. So here we have a statement of equivalency here that these two expressions are talking about the same thing. So a quick look at what do we see happening on either side of the equal sign. Well, on the left-hand side, there we go. So on the left-hand side, the 2 is being multiplied by 5, and the 2 is being multiplied by 3 before we add things together. So first we'll do the multiplication, and then we'll do the addition. On the right-hand side, with the parentheses, we're saying, hey, do the addition first, and then do the multiplication. So the only difference between these two equations is what do we do first, which of course ties to the order of operations. So in grade 5, so in 5th grade, and in Module 2 this year, we have used some similar reasoning. We've done some similar thinking to solve some problems. And the name of the property that we use to say that 2 times 5 plus 3 is the same as 2 times 5 plus 2 times 3 is the distributive property. And I vaguely recall kind of making a big deal about it being the distributive property of multiplication over addition and subtraction. So now let's take a look. We've looked at a specific example, so with numbers. Now we're going to step back here and we're going to say, does this work with variables? And how does it work with variables? So let's take a look and say, okay, what does this model represent in words? Well, I've got A plus B plus B that I could simplify into 2A plus B. So A plus B plus B, 2A's plus 2B's, or 2 times A plus 2 times B. Now what does 2A mean? Let's stop and think about this for just a second. Something we've worked on, we don't want to forget this. Well, hopefully your brain says 2A means that there are 2 A's, or 2 times A. Here's one of them, here's another one of them. And how many A's are there in the model? Well, interestingly, there's 2 of them. And how many B's are there? Well, there's 2 of them. So what expression could we write to represent the model? Well, 2A plus 2B. I know, quick review there. So in words, we would write A plus B plus A plus B. Looking at a different model here, notice that this one is different. So we've got A added to B and A added to B. And how many A's are there in the model? Well, 1, 2. And how many B's are there in the model? 1, 2. So what expression could we write to represent the model? Well, we've got A plus B plus A plus B, or we recognize this as repeated addition here and say, I am going to add this together over and over again. How many times? 2 of them. So here we have it written with those parentheses. And the question, of course, is, are they equivalent to each other? So here is the first expression that we built, and here is our second set of expressions that we built. Do I have 3 equal equations here? Sorry, expressions. Well, let's do a quick check just looking at the model. I've got an A and an A, that's 2 of them. I've got an A and an A, that's 2 of them. I've got a B and a B, that's 2. B and a B, that's 2. Without ever even looking at all of the expression stuff, I should be able to look at the picture and say, hey, I have the same stuff here. We know that the expressions that we wrote represent that stuff, which means yes, this expression is equivalent to this expression. They're talking about the same thing. All right. So we are going to use greatest common factor and the distributive property to write some equivalent expressions. So here is the question, and we probably need to do a little bit of unpacking here and say, okay, what is this question actually asking us to do? Well, the first thing they're saying is that we need to find the greatest common factor of the terms. So here, got our expression, and we want to figure out what is the greatest common factor of these terms. And then we're going to use that greatest common factor to rewrite the expression in a factored form. Which means, and this is one of those vocabulary things, the expression is going to be written as the product of factors. So we're going to change this up. We're going to use greatest common factor to write this. And the greatest common factor is going to be written outside the parentheses. So the first thing we need to do is ask ourselves, what is the greatest common factor? What is the greatest common factor of these terms? And to help us find the greatest common factor, we are going to write this expression and expand each of the terms. So we would write out 3 times f plus 3 times g, just like we've practiced in other lessons. Let's expand this out and see what factors we actually have. And then we can compare the terms and we can ask ourselves, what is the greatest common factor? What is the largest factor that they share? Well, in this term, I've got a 3 and an f, and in this term, I've got a 3 and a g. What factor do they share? Well, they share 3. 3 is the only factor they share, therefore it is the greatest common factor. So then, when it comes time to actually use the greatest common factor to rewrite this expression, we're going to factor the 3 out. We're going to take it out from both of the terms. And we're going to write it outside the parentheses. And f plus g is going to stay inside the parentheses. So this 3f plus 3g is equal to 3 times f plus g. Now I know one of the strategies that I showed earlier this year was working with things like this. And we asked ourselves, what can we divide both of these by? And this is how we found greatest common factor and said that 6 was the greatest common factor. This strategy works very well on these problems also. 3f plus 3g. A factor that I can divide them both by is 3. In this case, we're not just focused on the 3, though. We want to rewrite the whole expression. So I would say 3 multiplied by f plus g. So I am looking for common factors and I am dividing them out. And you'll notice here that this is written as a product. All right, so here's another example. So read and ask yourself, okay, what is it that they want me to do here? I see they want me to use the greatest common factor, and they want me to use the distributive property to write some equivalent expressions. So I need to find the greatest common factor. So they want me to find the greatest common factor of the terms. They want me to use the greatest common factor to rewrite the expression in factored form, which means the expression is written as the product of factors. And the greatest common factor is going to be written outside the parentheses. So I need to expand the terms so that I can find greatest common factors. Oh, but it looks like I didn't change this. It should be 6x plus 9y. 6x plus 9y. There we go. So do a little expanding here. And I could write this out. And this is where prime factorization comes in really handy. I could write this out as 2 times 3 times x, so there's my 6x, plus 3 times 3 times y. So I've used the prime factorization to break down these factors. Now, what do they have in common? Well, I see that they both have a 3. I notice that this one right here has a second 3, but it doesn't have a partner over here. When we're finding greatest common factors, we have to pull out things that have partners. So 3 is going to be the greatest common factor. And then the question is, how can I rewrite this? Well, I'm going to factor the 3 out, and it's going to be on the outside of the parentheses. That leaves me with the 2 times the x added to the 3 times the y. So you'll notice that I recombined what was left of the terms. After I took out the greatest common factor, I recombined what was left within the terms. I factored the 3 out. That left me with the 2, and that left me with an x. Factored the 3 out. That left me with the 3, and that left me with a y, and I recombined them. So I'll factor out the 3 from both terms, place it in front of the parentheses. I'll place what is left in the terms inside the parentheses. So here's the 3 coming out. Here's the recombined term, the recombined term. All right, so going to use greatest common factor in the distributive property to write equivalent expressions. So is there a greatest common factor in the terms in this problem? Well, to find that, I need to expand it out here and take a look at what factors I'm working with. So 3 times c plus 11 times c. Do my terms have any common factors? Well, I notice that in the coefficients, in the numbers, there's nothing in common here. But I do notice that in the variables, I do have a common variable. So the greatest common factor here is going to be the variable c. And I would factor that out. So when I expand, I see that each of the terms has a common factor c, written it out in the expanded form here. So if I'm going to rewrite this using the distributive property, I'm going to factor the c out, and I'm going to recombine what is left. I've got the 3, and I've got the 11. And of course, I always have the great urge here to combine the 3 and 11 to make 14 and actually have 14c. c times 14, which will be 14c. But that probably goes a little bit beyond what we want to be doing in this lesson. Yeah, they like us to stop here, which is okay. But it's kind of cool to look and be able to see what else could happen here. So the greatest common factor could be a number. It could also be a variable. All right, so use the greatest common factor in the distributive property to write equivalent expressions. Now this time, when you're done with the problem, you need to actually go through and give an explanation of how you did this. So go ahead, pause, rewrite this using the greatest common factor in the distributive property, and then take a look at the questions explaining your process. How did you do this? And when you're ready, unpause the video and continue. Well, first thing I did is I expanded each of the terms so that I could find common factors. And I found that I had 3 2's here and 3 2's here. And that made 8, the greatest common factor. So then I pulled that 8 out. So I took these and I moved them to the outside of the parentheses. And then I looked at what was left of the terms. And of this term, what I have left is a 3 times b. And on this term, over here, I've got nothing. So the question is, what am I going to do? Well, I know that there was actually an 8 here, and so somehow I have to have something to show that there was something there. So I'm going to put a 1 there. We're going to talk about that in a minute. I can't just have this term disappear. I have to show that it was actually there. It is an 8. And if I want to get an 8, I'm going to multiply 8 times 1. Like I said, we'll look at that in a little bit more depth in a second. So, a 1 in the parentheses. Here, that second has gone by. Well, when I factor out a number, I'm leaving behind the other factor that multiplies to make the original number. And this gets into the question of when do I need to pay attention to the factor of 1? Well, in this case, if I just take the 8 out and leave nothing here, I have pretended as though there was never an 8 there. So I need to use the 1, the other factor, to show that I want an 8 there. So in this case, when I factor an 8 out from 8, I'm left with 1 because 8 times 1 equals 8. So there are times when we have to pay attention to factors of 1. Now, how is this related to the first two examples? In the first two examples, we saw we could rewrite the expressions by thinking about groups. We can either think of 24b plus 8 as 8 groups of 3b and 8 groups of 1, or as 8 groups of the sum of 3b plus 1. So that shows that our two expressions are equivalent. And you can think about how you could do some model drawing to show this and prove it. All right, taking a look at some exercises here. So we are going to apply the distributive property to write equivalent expressions. So I'm going to look and say, hey, I can divide out a 7, which would leave me with x plus y. So I would have 7 times x plus y. Here I see I can divide out a 5, which will leave me with 3g plus 4h. And so I've got 5 times 3g plus 4h. Now I know that I've gone straight to this division method. If you need to write these out as prime factors, please do so. So 18 is 3 times 2 times m. And I've got 42, which is 2 times 3 times 7 times n. If you need to write this out so that you can see all of the factors, please do it. Please do not be too proud to do what it takes to be successful. And now I can look at these lists and look for common factors. Well, I see that I've got a 3 on this list and a 3 on this list. And I can see that I've got a 2 on this list and a 2 on this list. So I'm going to take the 2 and the 3 out and going to make a 6 with them. And then I'm going to look what is left. And I've got 3 times m. And over here I've got 7 times n. Make that plus sign look like a plus sign. All right, taking a look here, I can see that those are both divisible by 3. That'll leave me with a 10a and a 13b. So 3 times 10a, a plus 13b. All right, I'm going to let you figure out E through H. I've shown you two different methods. Once again, I cannot emphasize, if you need to go through the prime factorization process, you do it. You do that. And you'll notice, well, I guess before I go on, I should quickly point out that in these problems, you might have variables as your greatest common factor. I'm going to divide an f out. Don't forget that greatest common factors can be variables and numbers, or numbers. All right, so going to do a little comparison here. So we have to do a little substitution. So we're going to evaluate each of the expressions for x equals 3 and y equals 4, which means that I'm going to take this 3 and put in for x, so 6 times 3, plus, and then I'm going to put a 4 in for y, 21 times 4. And now I'm going to evaluate. I'm going to follow the order of operations. 6 times 3 gives me 18, and 21 times 4 gives me 84. And I will combine these together. 84 plus 18, add 10 gives me 90, plus 12 gives me 102. So there's one. And then I'm going to come over to this other expression. 3 times 3 times 3 plus 7 times 4. So I've done my substitution there. And now I work the parentheses inside. First, 9 plus 28. 3 times 9 plus 28 gives me 37. My brain is screaming at me that I think I did something wrong, but we'll see. 9 plus 28, 37. Yeah, I can't shake that feeling that I've done something wrong here. 6 times 3 is 18. 21 times 4 is 84. All right, 37 times 3 9 plus 2 gives me 111. And I'm going to have to apologize here because my brain is really screaming at me that something is not right here. 3 times, aha! I have typed in the wrong expression. This should be a 2x. So 3 times 2 times 3 plus 7 times 4, 3 times 6 plus 28, 3 times 34, and 34 times 3. Much better. So I apologize for that blip in the video, but there we go. Always make sure you copy down your problems correctly, otherwise things could go wrong. So both of these expressions were equivalent. So go ahead and try that out with exercise 2b. You are substituting in a 6 for g. Evaluate both expressions following the order of operations and see what you get. And repeat the process for 2c. And then take a moment and ask yourself, are there any patterns that you notice in parts A, B, and C? Well, hopefully you noticed, and my brain was screaming at me, hey, these are supposed to be equivalent. Hopefully you noticed that when you evaluated the expressions on each part, that the expressions were equivalent. And this shows that the two expressions are equivalent for the given values. So when I substitute in a 3 for an x in the equivalent expressions, that the expressions are equivalent. So what would happen if other values were given for the variables? What if we went back and we changed the x to a 5 and the y to a 3? When I evaluate, would I get equivalent expressions? Yes, because the two expressions in each part are equivalent, they are going to evaluate to the same number no matter what value is chosen for the variable. We have created a general expression, and no matter what, we've created two general expressions that are equivalent, which means as long as I'm substituting in the same value, so as long as x is the same in both expressions, I will have the same values. So, how can you use the greatest common factor and distributive property to write equivalent expressions? Think through your process here. How do you do this? All right, I can use the greatest common factor and the distributive property to change expressions from standard form to factored form. So we were changing 2a plus 2b, which is a standard form, into a factored form, 2 times a plus b. So standard and factored. So take a moment here and figure out what is the missing value that you would put in each of these to make these expressions equivalent. Five. Looks like they took a 9 out. Looks like they took an 8 out. Looks like they took 100 out. How did you find the missing numbers? I found the greatest common factor. And there's a variety of methods to do that. I can expand everything out. So that 4 times x plus 3 times 2 times 2 times y, and then I can break that 4 into a 2 times 2. Or, using a division method here, I can ask myself, what can I divide both numbers by? And I can start factoring that out using that upside down cake or the ladder, whatever you want to call it. I found the greatest common factor, and that's what I'm putting out here in front. That's what I'm dividing out. The greatest common factor of the two terms. This also, by the way, works with 3 terms, 4 terms, 5 terms. You have to find the greatest common factor of all of the terms to factor it out. All right, so an expression in factored form. An expression that is a product of 2 or more expressions is said to be in factored form. All right, so now that you've completed the lesson, hopefully you can show and explain writing equivalent expressions using the distributive property. Finding the greatest common factor, factoring it out, and then writing these expressions in factored form. How do we get to factored form? We find the greatest common factor, and we factor it out. We divide it out. All right, learning target. So we've looked at a quick relationship between addition and multiplication, the distributive property. And comparing expressions here, we had them in standard form and factored form, and we were observing equivalency, that they are equal. And in addition to that, we played with variables. So we did some experimenting with expressions and comparisons. We didn't do any prediction, but we played with the values, which I guess is probably a better fit here, when values within the expressions vary. So that concludes Module 4, Lesson 11. If you've got any questions, make sure you get with your teacher. Also make sure that you take the time to complete your problem set.